Thank you, Giacomo, for the introduction. So in this presentation, I'm going to, wait, there is the, okay. I'm going to introduce some works, some joint works with the group of Bologna, with Anderson, Davide, and Giacomo. And in particular, I will focus on this question. So probably you already know that, but I will just remind all the details that in the case of classical neural networks, we have a really interesting link between overparametrization and Gaussian processes that, in a certain sense, explain what was empirically evident before this result. So that classical neural networks are trainable and the training is successful. So in principle, we could have many doubts, I will discuss them, but finally, empirically and mathematically, it was possible to prove that in a rigorous way. So, starting from this idea, can we learn something more about quantum neural networks? Well, this is just the overview of what I'm going to say, and these are the two works on which my presentation will be based. So I will just introduce the notation. I will summarize the results of lazy training in the classical setting. I will introduce the architectures that we are going to consider for quantum neural networks, and then I will enter more in details in our results, in particular what happens in the case of quantum neural networks, and then some more peculiar properties of our situation that might not be present in the case of classical neural networks. So, as you know, probably way better than me, supervised learning, in particular, we are considering classification tasks, is just a way to learn from examples. So we want to reproduce the correct labeling of, in this case, some pictures, but in general, some input space. We are given a training set of example, and we consider a parametric class of function that I will call model. And training this class means minimizing an empirical cost function. So in all the talk, when I write L, I mean the empirical cost. And in particular, we will always assume to have a mean squared error, so a quadratic cost. That's not the most general case, but for some reason that you will see later, that's the one we really need in this case. So, as I said in the introduction, training classical neural networks is empirically successful, but there might be many doubts. So, first of all, training in the most simple case means just picking random initial parameters, random because we don't want to choose some particular case that might not work. We want to break any kind of symmetry. And then we use gradient flow or gradient descent in order to minimize the error on the training set. But of course, in general, the cost functions are highly non-convex, so there's no guarantee that we can achieve the global minimum. We could get stuck in a local minimum in general. Furthermore, let us suppose that for some reason we can achieve the global minimum. Well, is the model expressive enough to fit the training set? So one could wonder what happens in the limit of many parameters, more degrees of freedom. There will be more possibilities to fit the training set. But of course, when the number of parameters is very large, the risk is to overfit the training set. So, okay, we can achieve a global minimum, but this global minimum does not correspond to the original function that we want to reproduce. It just fits the training set, but outside is a really irregular shape that might be strongly dependent on the initial parameters and on the number of parameters. Just imagine a polynomial with really high degree higher than the number of examples. So what was proved for classical neural networks is that this is not the case. This is not the case. The overparameterized limit is regular. And in order to describe this scenario, I just need a technical definition that I ask you to keep in mind because it will be central in all the rest of the talk. So that's just a formal definition for mathematician. I will try to make it as intuitive as possible, but probably you're already familiar with it. A Gaussian process is just a family of random variable, a stochastic process. So in this case, the random variables are y, x is the label, which is fully characterized by a mean function and a covariant function. And it has the property that whenever we consider a finite subset of the labels, because it might be infinite in general, the probability distribution of this finite set of random variable is a Gaussian, joint Gaussian distribution having mean and covariance given by the mean and covariant function. So if I change the name of the random variables and instead of y of x, I call them f of x, you can imagine now that what we are describing are random functions. So every time we sample a Gaussian process, we are sampling an untier function, one of the three function there, for instance. Like when we sample a Gaussian variable, we sample a real number. Here, we are sampling something more general, an untier function, you see. And this would be a zero mean and Gaussian process with for each point a constant variance. But we could have something more similar to a function fitting some points. So you see in that case, the local variance in some certain points is zero. So we have a perfect fit of these points. And somewhere else, well, okay, every time we sample a function, we get something different, but at least very regular. Is it clear? Do you have any questions so far? Okay, because now I can explain just in a qualitative way, and then we will enter into the details for the quantum case, why the training of classical neural network in this regime turns out to be successful. Well, because the non-convex shape of the cost function, as the number of parameters increases, becomes more and more like this one, I would say. So with high probability on the random initialization the parameters, we will get to one of the global minima with just a small displacement. You can imagine if you have a really high number of parameters, each of them can change a bit, but these will sum up, because the parameters are a lot, will sum up to a macroscopic change in the function. And the each global minimum is a zero cost, so we have perfect fit. And the probability distribution, I mean probability distribution because there is a prior on the parameters, uniform, Gaussian, whatever you want, it depends. The probability distribution after the training will get more and more regular. It will become a Gaussian process fitting the training set. So we don't have the strong oscillation of overfitting, for instance. That depends on the number of parameters. So this is the classical result. If you have any question, otherwise I will move to the quantum setting. Yes, Antonio. Sorry? Okay. Well, there are some hypotheses that I'm not telling here. I will show in the quantum setting what's the role of barren plateaus, but I honestly I don't know which are the specific hypothesis of to avoid the corresponding case of variant plateaus in the classical. Okay, thank you for yeah, for clarifying this. Yes. Okay, so what about our case? Our model function will be given by a quantum neural network given by a parameterized circuit acting on an initial state given by this tensor product of 0. We use parameterized gates to encode the trainable parameters and the input. Well, this is just a specific example, but the input can be encoded also later in following layers, it doesn't matter. And at the end of the circuit, we have a final observable, which is given by the sum of local terms, local observable, single qubit in particular observable. Well, if you think that this is too specific, too restrictive, well, it's not, because we can generalize the result to a observable. We would just need more notation, more details. If you want, at the end, I can spend a few words on this, but just keep in mind that the fundamental idea will be the same, and it's more clear if we consider this kind of observable. So the model function will be given by the expectation value of this observable at the end of the circuit up to a normalization that I'm going to comment soon. So the fundamental quantities that characterize a given specific architectures are, first of all, the number of layers that may depend on m. M is the number of qubit. Given any parameter, we define the future light cone of the parameter as the set of observables which are affected by that parameter, that may depend on that parameter. And F is the maximal cardinality of a future light cone in a given architecture. And given an observable, we can define its past light cone as the set of all observable depending on that observable, not depending, that on which that observable depends. And so P will be the maximal cardinality of any past light cone in a circuit. And finally, as I said, there is a normalization. So writing the function this way as a sum of m terms, you see that we are adding more and more terms. So we want to keep everything to be finite. In particular, we want the covariance of the function to be order 1 at initialization. And so this is the definition of n of m. Okay, it can be rescaled by a constant factor, but let's say that the covariance is 1. It's like the sum of random variables, IID random variables that you need to normalize with 1 over square root of m. In general, n of m will not be 1 over square root of n, but it will have some corrections. Okay, let's move now to some more technical details about what overparameterization means for quantum neural networks. So in the classical case, it just means that layer by layer, you send the number of neurons to infinity, so the width to infinity. So we may wonder if it's enough to send the number of qubits to infinity in the case of a quantum neural network. Well, there's a simple argument that shows that since we have local observables, single qubit observables, then we could consider just the local Hilbert space involved in the computation of such observable. And if this local Hilbert space has polynomial or even constant dimension, then we could just classically compute the outcome of the observable, and then that would be not really an interesting circuit. So what we really want is an overparameterization not only in space, but also in time. So we also need to let the number of layers grow with the number of qubits, so that these light cones will grow as well, and the dimension of the local Hilbert spaces will increase with the number of qubits. Of course, it doesn't need to be proportional to the number of qubits. That's why I used another color. It might be suitably logarithmic. So what can we say about the model function when we randomly initialize the parameters? Well, if we write the model function in this form, you see that there is some kind of analogy with the central limit theorem. You know, you have the sum of fk of theta, theta are random variables, so fk of theta are random variables as well. And when we sum IID random variables, we have the convergence in distribution to a normal distribution, Gaussian distribution, with mean and covariance given by mean and covariance of the original random variables. However, here we don't really have real random variables, but we have a family of random variable parameterized by x, the input. So we have a family of random functions, but we already know that if we want to generalize the notion of Gaussian distribution to function, we have Gaussian processes. And another issue is that here we don't have an ID random variable, because you see, if you take the observable OK, and then you trace back the past light cone, and for each parameter you consider the future light cone, you will see that there will be more observables which has common parameters, and so in general they won't be independent. So the idea to face this problem is to consider, well, this work. I will not comment the technical lemma, but I will just give an intuition of the idea. When you have a family of random variables, you can build a dependency graph of this family of random variables. In our case, we can build a dependency graph of a circuit by connecting the observable which depends on each other. And you see the case on top is just the central limit theorem, while in the bottom you have an extreme case, the fully connected graph, where of course everything is dependent, and so you cannot really say what could be the limit. But if you are in the middle, it might look more like the empty graph. So the graph with no edges. And so in that case, we have an approximated version of the central limit theorems that, provided that this graph has a degree, a maximal degree, which is not too large compared to the total number of random variables, well, we still have convergence to a Gaussian process, a random variable or process. So under the hypothesis that the light cones are narrow enough compared to the normalization, the initial function, the function generated by the quantum neural network at initialization, will converge in distribution to a Gaussian process with zero mean and covariance given by the specific architecture of the circuit. So what about the training? Can we characterize the training dynamics analytically? Well, I will just recall my notation. D was the training set. X now will be the vector of the input of the training set. Y will be the vector of the corresponding outputs, gradient descent. By simply applying the chain rule, we can get an evolution equation for the model function in terms, which is written in terms of this quantity, which is called empirical neural tangent kernel, and then the function itself. As you can see, the form of the equation doesn't have a simple solution in general, because it's derivative of f, something which depends on time, and then multiplying f. So in this case, we cannot give a immediate answer to what is the solution of the evolution of the model. Yes. Oh, sorry. Great question. I will spend some words later. I have some. Thank you so much for this question, because that's the difference between quantum and classical. For the moment, for the moment, zero error. We assume that we performed an infinite number of measurements and we have access to the expectation value. Exactly. So what can be proved? It's not hard to prove that studying this equation is possible to show that what was I suggesting before? The number of parameters is large, so then a small evolution is sufficient already to reach a shape which fits the training set. So this gradient of the cost will become soon zero. So in other words, we will have lazy training. The displacement of each parameter will be asymptotically vanishing when the number of qubits increases. As a consequence, so if the displacement in the parameter space is tiny, we could consider a first order approximation of the model function, which is just a mathematical tool. I'm not saying that this has necessarily something to do with the original one, but at least is an approximation that we could study, and we could just see what happens if we evolved this linearized model instead of the original one. Well, you see, the differential equation now is different. Now it's easy to solve, because it's just derivative of f is something constant multiplied by f. And so here you have the analytical solution, just an exponential decaying solution that maybe it's not immediate to see, but converges to y. So it's perfectly able to train to fit the training set. And it's written in terms of the function at initialization. Therefore, being a linear combination of Gaussian processes, it's a Gaussian process itself. So the last ingredient is to show that indeed this approximation is a good approximation. So the two trajectories are asymptotically equivalent. And so here, instead of saying that it's the linearized model to converge to this solution, well, also the original model satisfying the original equation will converge to the same solution, that being a linear combination of Gaussian processes is a Gaussian process itself. So that's the statement of the theorem, provided that the light cones are narrow enough with respect to the normalization, that these empirical neural tangent kernel as an expectation value converges to something, and that's quite general. Okay, one could find some pathological example. For instance, you do not encode the input. Of course, it will not be invertible, but you want to encode the input. So in general, this should not be an issue. And in that case, we have yes. L is the number of layers. M is the number of qubits. F is the maximal cardinality of a future light cone of the architecture. Future light cone is just given any parameter, you see the number of observables depending on that parameter. And P is the past light cone, so you do the same thing but fixing an observable and looking back the number of parameters that contribute to that observable. I will show you an example with some numbers later to comment what are these quantities concretely. So, but you can imagine if the number of layers is logarithmic, then the future and the past light cone will be some polynomials of a logarithmic function. So you see, it's n of m is square root of m or some small correction to it. So, for instance, for logarithmic depth, it's satisfied. Unless you use non-local 2-qubit interactions. In that case, you have to tune a bit better and check if it is verified or not. So exponential conversion of the cost to zero, exponentially fast in time. Regularity, well, this is just the Gaussian process, the mean and covariance function of the trained network. And so these results are somehow similar to the classical case, but of course with different techniques and different in a different context. So your question, noise, yes, because we define the quantum neural network to be the function generated by the quantum neural network being an expectation value of a quantum observable. So in general, there will be some statistical noise because we cannot sample it an unlimited number of times, and we want to make sure that the required number of measurement grows polynomial in the number of qubits. Otherwise, if it's exponential, then it's useless. So in order to do that, we need to move to a discrete time evolution equation, which is what empirically we do. And instead of using the derivative, the gradient of the cost function, we will use an estimator, unbiased estimator. This is possible using parameter shift rules. It's not a problem. There's no bias. But anyway, the fundamental idea is that if we want to achieve epsilon small cost, we just need, what we proved is that we just need to have a sufficiently small variance of this estimator. And in order to have this sufficiently small variance of the estimator, the number of measurements, it's a constant in all these parameters, but in terms of the number of qubits, is something that grows polynomially. So a polynomial number of measurements at each time step, and there is an upper bound, is sufficient to ensure that with probability of failure probability at most delta that appears in this constant, we will get all the previous result, fit, Gaussian process, and so on. Yes. Yes. No. No, the light cones doesn't need to be the light cones are in general, if the light cones are not polynomial, the hypothesis of the previous theorem cannot be satisfied. If the light cones are exponential, the normalization will never be exponential. So this quantity was supposed to go to zero in the hypothesis of the previous theorem. It's the first hypothesis there. Yeah. But so this quantity was required in the hypothesis to go to zero, and this quantity is polynomial. So it's polynomial. That's what so here you have an example finally, because the idea now of this slide is to discuss a bit the problem of barren plateau, also to answer Antonio's question. So it's possible to prove that there is a link between barren plateaus and this normalization constant. In particular, the vanishing gradients in this kind of circuits are related to the growth of the number of layers. So we know that if the number of layers is linear or more than linear, we may have barren plateaus, but if it is proportional to the logarithm of the number of layers, we will not have barren plateaus. And in particular, this normalization constant depends, like for the case of barren plateau, I'm just using the estimates of this paper, depends exponentially in L. So taking L to be epsilon logarithm of M, and considering a circuit which is at least two-dimensional, and you will soon see why. Well, it's clear, because if it's one-dimensional, then the light cones are polynomial, and then also the local Hilbert space have polynomial. So the light cones, sorry, are logarithmic, and the local Hilbert spaces are polynomial, and so in principle we could have an efficient way to simulate them. But if it's at least two-dimensional and epsilon is small enough, then L is logarithmic, F is some power of logarithm of M, you see it on the future light cone. P as well, the past light cone depends on the number of layers, and it's as well a power of a logarithmic, so a logarithm. And you see, replacing there and using the constraint of epsilon is to the power of 6ce divided by 2. And then finally you have that the hypotheses are satisfied, because this is just polynomial. The term growing is polynomial, and this is of logarithm, and this is just a power of M. And the fact that we use that 2D square lattice means that the local Hilbert space are not trivially polynomial. That's the idea. Yes. Yes. Is-
As in, do you know if all of your parameters are contributing to the gradient here, or is it like mostly parameters for your survey?
Okay, I see. Well, so you mean not all the parameters are contributing to the... Well, in principle, I don't see any reason to exclude that all the parameters are affected. But anyway, yes, one could use the lazy training quantitative bound to see the displacement of each parameter. So you have a upper bound on the displacement. Then use the Lipschitz constant of your model function and you ask that the product of the displacement and the contribution of the maximal growth of the circuit is macroscopic, so that it can fit the training set, and in this way you can find a fraction, or at least you see what is the fraction that must of the parameters that must contribute, because you have the lazy training constraint. So this way you can somehow reverse engineer and find out if the fraction is relevant or is just smaller. Yes. Yes.
Yeah, in this particular program, do you have the exponential concentration or not?
Exponential concentration? So you mean barren plateaus? No, in this case, we don't have barren plateaus. You? Sorry.
In the space, I mean, if you add one key and you look at the right point of log-n sequence, is log-n qubits, so exponential log-n is here, and you don't have exponential.
But you have to consider the exponential of the number of layers, not of the light cones. So that's to compute the local Hilbert space. So you consider the exponential of the light cones when you want to compute the dimension of the local Hilbert space, to say that it's not trivially polynomial. But when you want to lower bound the gradients, or an upper bound, I mean, all the computation of quantitative barren plateau depends on the number of layers, not on the light cones. In, no, but you have to use the, yeah.
But I think, okay, so this, from what I understand of this John Knott paper, it's been a while. It's like, the total gradient contribution is not exponentially vanishing, but what might be happening is like some parameters that aren't so far back from your observable are what are like really contributing the most to your gradient or something.
So here you can find really the quantitative upper and lower bounds for barren plateau that just turn out to depend on the exponential of the number of layers, not involving, in that case, light cones. That's why there is this difference between dimension of the local Hilbert, because dimension of the local Hilbert spaces and exponential of the number of layers in outside the one-dimensional regime are not equivalent. That's the difference. Yeah, I don't remember if there was the hypothesis of nearest neighbor interaction. I'm not sure. I don't think so, honestly. But I don't think there was a hypothesis of nearest neighbor interaction. Not sure, but at least in that situation, it's sure that was the dependence. So the gradients were vanishing with 1 over exponential of number of layers up to a constant. So, well, just as a final remark, we described a sequence of circuits, but in practice we have a given finite size circuit, so we would need to understand how far is a given circuit of a given size from this ideal limit of Gaussian processes. And well, first question that we should ask: what is the right notion of discrepancy between the probability distribution of a given circuit and another target distribution? Why? Well, because you see, if we want to compare to probability distribution, a first guess could be, let's use the total variation distance, which is just the classical version of the trace distance. So this distance just quantifies, so these are P and Q probability distribution over the label f of x of root x. So it's really our case. So this quantifies somehow the overlap between the two probability distribution. And you see in this case, the two probability distribution are more or less both peaked around +1, but the overlap is quite small. So according to this distance, we would say that they are quite different. But well, for a classification problem where you care, for instance, just about the sign of the function, these are more or less equivalent. So that's not really the right distance to use. And you can think from an extreme perspective, if you just want to compare some Dirac deltas, P and Q are as distant as R and Q, and the distance is maximal because there's no overlap. So you see, this is not the right notion, because P could be a good approximation of Q. It has the same sign, it's close. R is a wrong guess. So how can we take into account the distance of this probability distribution? So think about being in Paris, and you have some bakeries and some coffee shop. You need to transport the bread from the bakeries to the coffee shop, and you will pay the transportation cost. And your idea is that you want, of course, to minimize the cost, to find the most effective way, efficient way to move this mass from an initial distribution, which is the blue one, to a final distribution, which is the red one. So mathematically speaking, we want to displace the original distribution P to the final distribution of Q, knowing that the cost of moving y to y prime is given by this function. If you want to move a unit mass from y to y prime, we'll pay C of y prime. And you want, of course, to minimize this cost over all the transportation plans, the way to move this mass. And you see that in this case, P and Q are close, while R is very far, because you have to make a long travel before reaching P or Q. And okay, we consider in particular also a threshold, because this is technically useful to not care so much about tails. If we have a tail of R that we cannot really bound, that we don't want to care, that's a technical solution to get rid of it. But it's also meaningful, because you see R and R prime, which are after the threshold, are both wrong guess. And it's not really important to say that if R prime is more on the left, the guess is extremely wrong. Okay, it's wrong. That's enough. It's a classification problem. It's not the right guess. So you see, it's a technical aspect, but it's really reasonable, and also operational speaking. I mean. So the quantitative bounds that we give are always of, well, comparing the effective distribution of x to the ideal Gaussian process, are always written in terms of normalization constant and light cones. And under the hypothesis of the previous theorem, this converges to 0, and there is also a constant depending on the specific parameters of the of the circuit and in general of the supervised learning problem. So, well, just to summarize, we saw that the limit of infinite width for quantum neural network produces Gaussian processes at initialization and also after training. The training is under some hypothesis successful, so it's stable under statistical noise. It requires a polynomial number of measurements, and it ends up with a perfect fit of the training set without overfitting. This regime can be quantitatively upper bound, and the statement that we gave in particular, I did not emphasize, but are not valid, okay, for just with high probability of random architecture. No, no, no. Given any fixed architecture that we operationally randomly initialize, but initialize the parameters of the architecture, not the architecture itself is random. Well, in any case, in each case the hypotheses are satisfied, these statements will hold. So it's not just something with high probability over random architecture. And finally, these results are a first step, a first attempt to link initialization to the training, analytically. So you can immediately imagine all the open questions. So can we control the non-Gaussianities? Can we lower bound them? Or at least can we understand a bit more about their role? Can they be useful? Is it possible to study the training dynamic outside this simple regime where you saw that the differential equation can be easily solved? Is there a strategy to classically simulate the Gaussian regime or non-Gaussian regime? So the connection between initialization and trained network is a first step to understand when initialization is computable classically, means that also the trained network is computable classically. And in particular, we are working on giving the minimal reasonable hypothesis to provide classical simulation at initialization and therefore also after the training. Are there, on the contrary, algorithms that can be retrieved by training these networks? Can non-Gaussian correction play an important role? These are all open questions. So before the break, let me just invite you for an unofficial, non-authorized disclaimer. The organizing committee is not involved in this and it's not responsible. Let me invite you to an official social run in the city after the poster session. If you want to join, just let me know. Thank you for your attention.
Questions? Any comment? Remember that we have 35 degrees.
Yeah, but at 6 it will be 31, 32. Yeah.
You mentioned when you had your flash the weak squared error or something like this, that this was important.
Yeah.
Your analysis. So what, like,
why? So the reason is here. When you write down the gradient flow equation in terms of the gradient of the cost function, then this gradient is linear when you transform it into a function, differential equation for a function. You see, it's linear in the function itself. And if you consider general costs, the derivative of the cost might not be linear in the function. So even assuming to have a lazy regime, this equation might not be Yes, quadratic, because then all these properties, it might work for other, but it's not as immediate as in this case. Seven. Which seven? This seven? Yes, this one? No. What? Okay, I see. Graph class. So the idea is that you consider as vertices of the graph the labels of the random variables. Then whenever so it in this case it's just enough to connect the random variables which are dependent, but the theory more in general was that if you consider two sets of random variables and they are mutually dependent, then there must be an edge connecting these two sets. So it was a bit more involved the original definition of dependency graph, but for quantum circuit in this case it was more simple. There were not counterexamples of random variables which are pairwise independent, but if you consider the three of them, they are dependent. So okay, it's more subtle than what I presented. And that's enough, because then you just need to consider the maximal degree of the graph, and you have a quantitative upper bound on the cumulant of the random variables of order R. The degree, yes, the degree and the number of vertices n, and R, which is the degree of the cumulant, and A, which is the uniform bound on the random variable. These are all the quantities which are needed. Yeah.
The initial parameters can they be highly correlated?
No, they are IID at least. So, well, I mean, yes, yeah, because you mean to avoid the okay. So, yeah, okay. So, for the first theorem, we assume the parameters to be IID. For the training part, it was useful for some reason that I don't remember now to assume that they were to be uniform. Then we assumed them to be uniform. It was just a technical assumption. No, IID, of course, but uniform during the training, I don't remember exactly why. Maybe there was just I think to upper bound the normalization of the neural tangent kernel. That doesn't matter. To generalize this setting to correlated parameters, I would just say that you need to introduce the correlation in the dependency graph, to use the same quantitative bound with the new degree of your new graph. And then you have to check that these cumulants are such that the non-Gaussianity will disappear. And in that case, you have a Gaussian process. That's the only ingredient. So I would say, yes, you can consider this case. We did not, because of course it really depends on the correlation that you have, but just introduce them in the dependency graph and you are done. It depends if they